Okay, I hope I'm audible to all the students who are attending this lecture. Okay, we start with a new topic today in mathematical methods in economics, part 1. This is called relations. Okay, in the last few lectures, we were doing preliminaries, if all students can recall, which consisted of set theory and symbolic logic. We start with relations today. So before understanding relations, let us first understand what is meant by Cartesian product. Let us understand what is meant by Cartesian product. So all students, let's write the definition of this in your registers. Let capital X and capital Y be two non-empty sets. Let capital X and capital Y be two non-empty sets. Then define their Cartesian product. Define their Cartesian product X cross Y as the set of all ordered pairs small x and small y such that the element small x belongs to the set capital X and the element small y belongs to the set capital Y. So I can say that is X cross Y is the set of all ordered pairs. It is the set of all ordered pairs of the form small x comma small y such that small x belongs to the set capital X and small y belongs to the set capital Y. So the Cartesian product concept students have done in high school also. It's not a new concept for you. Capital X and capital Y are two non-empty sets. Non-empty means they are not equal to 5. They contain elements in them. Then the Cartesian product will be the set of small x comma small y, where small x belongs to the set capital X, small y belongs to the set capital Y. Guys, remember that small x and small y are elements. Capital X and capital Y are sets. Let's write a note. If the set X consists of m elements in it and the number of elements in set Y is n, then the number of elements in X cross Y will be m into n, where OX denotes the number of elements in X, OX denotes the number of elements in X, OY denotes the number of elements in Y. So if the set X consists of m elements and set Y consists of n elements, then the Cartesian product X cross Y will consist of m into n elements. The second note, Cartesian product of X cross Y is not equal to Cartesian product of Y cross X. So all students should understand this, that if I do Cartesian product of X cross Y, that will not be the same as Cartesian product of Y cross X. And the third point which all students should understand, in particular, X cross X will be what? x cross x will be the set of x comma y such that both x and y belong to the set capital X. So when we talk about Cartesian product of x cross x, it is the set of x comma y such that both x and y belong to the set capital X. So I hope all the students attending the lecture have understood the definition of Cartesian product and the 3 points in the note.
So,
Please ask your doubt.
so okay, bracket में जो x लिखा है that should be capital X ना, because it denotes the number of elements in the set X.
So I can make it like this. I can make it like this. You can unmute your mic. I can make it like this. Capital X and capital Y. If the set X consists of m elements and the set Y consists of n elements, then the Cartesian product X cross Y will consist of m into n elements, where OX is the number of elements in X, O capital Y is the number of elements in Y. So I hope all students are clear with the definition and the 3 points.
Sir, can you please give me the numerical example of this?
We will be doing the numerical example in just a minute. So I'm quickly revising it with all the students. Cartesian product of x cross y will be the set of small x and small y such that small x belongs to capital X and small y belongs to the set capital Y. If the set X consists of m elements and set Y consists of n elements, the Cartesian product consists of m into n elements. Cartesian product of x cross y is not equal to Cartesian product of y cross x, and Cartesian product of x with itself is the set of x comma y such that both x and y belong to capital X. Now let's do a practice question on this. Let's do a practice question. So given the set A as A, B, C, set B is given to us as 1, 2, and set C is given to us as alpha, beta. The question asks us, find Cartesian product of A cross B, find B cross A, find A cross A. Then they ask us to find A cross B cross C. So let's find all of them one by one. So Cartesian product of A with B will be, let's start from A. So A1, comma A2, comma B1, comma B2, comma C1, comma C2. So Cartesian product of A cross B is A1, A2, B1, B2, C1, C2. If I find Cartesian product of B cross A, B cross A will be, B is 1, 2, A is ABC. So Cartesian product of B cross A will be 1, A, 1, B, 1, C. 2, A, 2, B, 2, C. So you can clearly see that A cross B is not equal to B cross A because internal order matters. A comma 1 is not equal to 1 comma A. A comma 2 is not equal to 2 comma A. So internal order matters. So you can see that A cross B is not equal to B cross A. Now guys, if I find A cross A. It is the Cartesian product of ABC with itself. This will be A comma A, then A with B, A comma B, then A with C, A comma C, then B with A, BB, BC, CA, CB, and CC. You guys, you can also observe one thing. How many elements are there in A? Set A consists of how many elements? 3 elements. Set B consists of how many elements? 2 elements. So Cartesian product of A cross B consists of how many elements? 3 into 2, which is 6. You want to count them, you can count. 1, 2, 3, 4, 5, and 6. Similarly here, A consists of how many elements? 3. So Cartesian product of A cross A will be consisting of how many elements? 3 into 3, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I hope all students are clear with the numerical example. Also, why is A cross B not equal to B cross A? Because the internal order is disturbed. When I talk about internal order, it means the terms in the brackets. Guys, A comma 1 is not equal to 1 comma A. The two are different. Similarly, A comma 2, the ordered pair A comma 2 is not equal to 2 comma A. So that is what all students need to understand. So A cross B is not equal to B cross A. Then we can also find the fourth part. So let's find the fourth part. We have calculated the first 3 parts. Let's find up the fourth part. A cross B cross C. That means set of ABC with set of 1, 2 into set of alpha beta. So guys, let's first solve the term in the brackets. So this remains the same, but this will be 1 alpha, 1 beta, 2 alpha, 2 beta. Now I have to do this cross this. So it will be A comma 1 comma alpha, A comma 1 comma beta, A comma 2 comma alpha, A comma 2 comma beta, and I can go on. You all can write this in your registers. You all can further complete it. Same will go for C also. I hope all students have understood the numerical example. We have found out A cross B, we found out B cross A. We found that A cross B is not equal to B cross A. We found out A cross A, and right now this is nothing but A cross B cross C. First we find B cross C, then we further do it with A, and then we get this whole term. So I hope all students are clear with this. Then let's write a note. All students, let's write a note. A cross B will be equal to B cross A when? Only when A is equal to B. Only when set A is equal to set B. If two sets are equal, if A and B are equal sets, A cross B will be equal to B cross A. Second thing, guys, suppose you can see, write this. Suppose my A cross B comes out as A comma 1, A comma 2, B comma 1, B comma 2, C comma 1 and C comma 2. Suppose my A cross B comes out as this, and suppose my X is this. A comma 2, B comma 1, C comma 2, A comma 1, C comma 1, B comma 2. The question I ask you is Cartesian product of A cross B equal to X? So when will they be equal? They will be equal if the internal order is not disturbed, but external order can be disturbed. Look on to the statement I'm speaking. A cross B will be equal to X if the internal ordered pair is not disturbed, but externally it can be disturbed. For example, if I have A comma 1 here, I should have A comma 1 here, but that doesn't matter where it is. If I have A comma 2, A comma 2, B comma 1, B comma 1, B comma 2, B comma 2, C comma 1, C comma 1, C comma 2, C comma 2. So answer is yes. Cartesian product of A cross B is equal to X. Because even though the order of the elements is disturbed, even though the order of the elements is disturbed, but the internal order, that is the sub elements are not disturbed. So you can clearly see, guys, if instead of A comma 1, if I would have had 1 comma A, suppose I would have had 1 comma A, then A cross B would have been not equal to X, because the internal order gets disturbed. But if instead of 1 comma A, if I have A comma 1, then A cross B will be equal to X. So I hope all students have understood the concept of Cartesian product. With this, the concept of Cartesian product is over. So now we are starting with the main thing. So now your heading is relations. So let's write the definition. A relation R from X to Y. A relation R from set X to set Y is a subset of the Cartesian product X cross Y. Now, all students from my lectures on set theory know what is the definition of Cartesian product. I hope all students know that. Also, all students know what is meant by a subset. So a relation is a subset of the Cartesian product. That means a relation lies within the Cartesian product. I can write it like this. Relation is a subset of the Cartesian product. You want me to explain you using an example? Let's look at this example. Let capital X be equal to x1 comma x2 and capital Y be equal to y1 comma y2 comma y3. Then if I ask you what is x cross y, the Cartesian product, you all will be able to answer now, x1 comma y1 and so on. I am writing it. Okay, this is my Cartesian product. This is my Cartesian product, right? Now any subset of the above Cartesian product, any subset of the above Cartesian product x cross y will constitute a relation. Example, let us take a subset of it. Phi is a relation because all of us know that phi is a subset of every set. We know this, right? Recall, phi is a subset of every set. So phi is a relation. Another relation, set of x1 comma y1 and x2 comma y1. Randomly I have taken. This is also a relation because it is a subset of x cross y. I can take another one, x1 y2, x1 y3, x2 y2. x1 y2, x1 y3, x2 y2. This is also a relation because this is also a subset of x cross y. I can take the whole thing itself, R4, which is the whole thing. Let me write the whole thing. This is also a relation. Why is this a relation, guys? Because every set is a subset of itself. So all of these are examples of relations. Why? Because R1, R2, R3, R4. If you observe them, R1 is also a subset of x cross y. R2 is also a subset of x cross y. R3 is also a subset of x cross y. And R4 is also a subset of x cross y. So what we learned today is that a relation is nothing but a subset of the Cartesian product. Okay, let's write a note. Let's write a note. Let us write a note now. If the ordered pair x comma y belongs to the relation R, then we say that x is related to y. What does this mean? This means that element x is related to element y. If x comma y belongs to R, we say that element x is related to element y. Okay. Second note. in particular, a relation R on X is a subset of the Cartesian product X cross X. So guys, when I say consider a relation on X, what does this mean? If I say, look at the statement, consider a relation R on X. What does this mean? This means that R is a subset of X cross X. So what I'm trying to do is, since all of you have now come to college, I am trying to make you comfortable with the mathematical symbols we will be using. So whenever I write in the question, consider a relation R on A, what will that mean? R is a subset of A cross A. Consider a relation R on Z, it means R is a subset of Z cross Z. So I hope all the students have understood this. Okay. So now let us do the type of relations. So our heading now is types of relations on X. Okay, so let R be a relation on X. Guys, what does this mean? That is, R is a subset of X cross X. Then R is said to be, point number 1, reflexive. If and only if X is related to itself for all small x belonging to the set capital X. That means a relation is said to be reflexive if every element of the set X is related to itself for all small x belonging to the set capital X. Example, suppose X is equal to 1, 2, 3, 4 and consider the relation R1 as set of 1, 1, 2, 2, 3, 3, 4, 4. Is this a reflexive relation? Yes, because every element is related to itself. So I can say that R1 is a reflexive relation. Why? Because every element of the set X is related to itself. By the way, guys, if I say that consider a relation R on X, then what will R be? R will be a subset of X cross X. That means in this case, any relation, in this example, any relation we define would be a subset of 1, 2, 3, 4 का Cartesian product with 1, 2, 3, 4. Because when I say consider a relation R on X, It means R is a subset of X cross X. What is X here? 1, 2, 3, 4. So any relation we define will be a subset of 1, 2, 3, 4 ka Cartesian product with 1, 2, 3, 4. Now this is a reflexive relation. But guys, suppose I define another relation. Suppose I define another relation. Is R2 reflexive? No, not reflexive. Why? Because 4, 4 does not belong to R2. So the point to understand here is that it has to be for all. It has to be for all, not for one. So this is not a reflexive relation because 4, 4 is not there. But suppose I write it like this. Suppose I write it like this. Is this a reflexive relation? Yes, this is reflexive. Why is it reflexive? Because 1, 1, 2, 2, 3, 3, 4, 4, all of them belong to R. So this is a reflexive relation. So I hope all students have understood this. Moving on to the second type, symmetric. Symmetric. So a relation R on X is said to be symmetric if and only if X is related to Y, it implies Y is related to X. For all small x and small y belonging to the set capital X. Remember, whenever I write in small letters, elements. Whenever I write in capital letters, sets. So symmetric relation means that if X is related to Y, Y should also be related to X. All students remember P implies Q. Students who have attended my lectures on symbolic logic. It's like the same thing, P implies Q. Let's take the same example to understand this. Suppose X is equal to set of 1, 2, 3, and 4 and define the relation R1 as 1, 1, 2, 2, 3, 3, 4, 4, 1, 2. Is R1 symmetric? First of all, is R1 reflexive? Yes. We know why it's reflexive. Because 1, 1, 2, 2, 3, 3, 4, 4 all belong to R1. Is R1 symmetric? Not symmetric. Why? Because 1, 2 belongs to R1. But 2, 1 does not belong to R1. 1, 2 belongs to R1, but 2, 1 does not belong to R1. That is why this relation is not symmetric. Suppose I had this. Suppose I had this. Now is it symmetric? Yes. Now it's symmetric. Because if 1, 2 belongs to R1, then 2, 1 also belongs to R. Now guys, understand what I am doing. I am erasing both. I ask you, is this symmetric now? Is it symmetric? Can any student answer this? We know it's reflexive. Is it symmetric?
Yes, sir.
Why?
So because the elements are same, so the order doesn't matter.
So Unmute your mic. Let me explain you in a better way. All students who have attended my lecture on symbolic logic, if you recall, on the top I am writing it. When we had done this implication P implies Q, remember, if I say that P itself is false, suppose P itself is false, do we need to worry about the conclusion? Answer is always true. What was this concept called as? This was called as the concept of vacuously true. This was called as the concept of vacuously true. Vacuously true. So if the hypothesis itself is false, do you need to worry about the conclusion? No. So in this, is X related to Y? In this, is X related to Y? No, X is only related to itself. So if the hypothesis itself is not holding true, by default, it is symmetric. By default, it is symmetric. So when will it not be symmetric? It will not be symmetric if 1, 2 belongs, but 2, 1 does not belong. But 1, 2 itself is not there. Hypothesis itself is false. X is not related to Y anywhere. X is related to itself only. So if the hypothesis itself is false, we don't need to worry about the conclusion. The statement will be true. That means the function is, that means this is symmetric. So I hope all students have understood this. This is by default symmetric. And so guys, this is where I stop in the lecture right now. In the next lecture, we will discuss the further two types of relations. It's not over yet. In this lecture, we have discussed the reflexive property and the symmetric property. So I request all students attending this lecture, please leave the meeting and join back again using the same link. I repeat, leave this meeting and join back using the same link. This is where I stop.